Thank you all for being here. Welcome to this session about software deployment and development. This will be a short session, but there will be a large number of topics. So obviously I won't be able to go into details for all topics, but I will give you a large number of pointers and references. I would like to start with a little question to you. Do you know what this is? Do you know what this is? Yes. It looks like a periodic table of elements, but actually it's not. It's a list of software that people use when they need to write software. So actually, the goal of this session is to promote the tools that the professionals are using to write and deploy programs and make them correct, maintainable, shareable, and fast, all of this efficiently. And so in the slides that are coming, we will look into each element of this sentence in turns. And we will start with the first part, which is how to make programs correct, maintainable, and shareable. And actually, there's a whole literature about this. So this is a research topic, how to write correct software. So I give here some references if you want to go into details, but basically here is a summary of each good practice that you need to follow if you want to make your program correct and maintainable. And I will go into details into all of this one by one. And the first and the most important advice is to write for humans, not for computers. And the rationale is that most of the time when you need to write software, you spend at least 10 times more time reading the part of the code that you have already written than you are writing new code. So actually, it's very important that your code is readable so that you can easily navigate in there and make changes. And here is a little example of two pieces of code that do exactly the same thing, but this one is less obvious than this one in terms of what it's doing, because you see the variables have short names. You have hard-coded constants here, while here you see that the constants have been assigned to a variable that has a name which is intelligible. So if I show you those two codes, those two pieces, you already immediately can understand what this is doing, why it is doing, while here you just see three loops, but you don't actually get immediately the meaning of what is the intention. But here the structure is clearer. You have three loops, three integrated loops, while here, because the variables have such long names, the structure of the code is less obvious. And so there is a sweet spot in between those two structures. Good names are very important. They allow you to give to necessitate less comments, and there's a lower cognitive burden on the people who are reading the code if you are choosing the names correctly. What you need to avoid is what we call naming anti-patterns, which are described here. Every time I take something from the literature or from a reference, you will see the reference here. You can dig deeper if you want. But basically, these are bad habits that some people tend to have when they write software. For instance, the first one up there, you see, naming something get something will let the reader to assume that this function will retrieve something, retrieve an object, for instance. So it's important that this function does that and not something else. So here the anti-pattern is naming something getting a function that it does more than getting, that maybe has a side effect or something like that. It might be clearer with the second example, which is anti-pattern of naming is something that does not return a Boolean. When you have a function that says is lower than, you assume that this function will return a Boolean value, true or false. If this function returns an integer, it will make it harder for the people who try to understand the code to actually get what is going on. And here is an example of the problems that can arise if you don't take into account the reader when you write code. I don't know if you know about Stack Overflow. It's a large website where people who write software can go to ask questions when they are stuck. And people can vote on questions. And this is a quite highly voted question, which reads, what does this operator do in C? So who knows about C here? Who can read C? A few people. Those who know about C, do you know what this operator is? Never seen? No, it's a valid C construct that can be used in a construct like this. And so the person who asked the question, they saw this in some piece of code, but they were not able to understand anything about what it was doing. And they were not alone. There were more than this amount of people who were confused about this construct. And actually, it's just a different way of writing this. And I'm sure this, even if you don't know C, if you have never learned C, I'm sure you can understand that there's a condition. And if the condition is true, there's something that is going on. This is nicer to the compiler because it avoids some branching techniques that can have negative impact on performances. But this is much easier to read for the human. And this is what you need to prefer over the version that is unreadable. So you see the idea when I say you need to write for the human, not for the computer. It's important that even yourself in 6 months, when you read your code, you need to understand what is going on. About writing, you need to learn an editor and know it inside out. Maybe you attended the Vim session. So Vim is nowadays the second most popular editor, and the most popular is Visual Studio Code, which is also a very nice alternative. The best way is to know both of them, because you can use Vim syntax into Visual Studio Code, and that is the nicest combo that I know of and that I use. And writing is important to choose a correct language. So here are 5 examples of languages, programming languages, that are totally valid in a scientific context. What we like about them is that they have a computation efficiency concern. So they are written in a way that computing resources are correctly used. They have optimized libraries available for linear algebra, for synaptic processing, for machine learning, and so on. So it's important that you don't write those by yourself, so that you use a language in which those libraries are available. They have a support for parallel computing. It's important because the clusters, they have parallel machines. If you want to use all the power of the cluster, you need to write parallel software. And all of them have extensions or libraries for using GPUs or accelerators. If the language that you want to use does not have these features, it will be harder for you to write software for running on the clusters. So these are the typical languages that you will find on the clusters. I just would like to mention to you 2 additional languages which are not classic in the HPC world, but I believe they will come soon. They are Haskell and Scala. The big difference between those 2 languages and the languages that you've seen before is that they are functional programming languages, meaning maybe you've heard the sentence that in Python, everything is an object. Here in Haskell or Scala, everything is a function. And actually, the way that they work is very similar to the way we write equations on paper. They are very close to the mathematical formulation. And the constraint that they impose on the code make it so that actually, whenever it compiles, you are nearly certain that it's correct, because there are no side effects and everything is clear. And it's also easier to make parallel because there are no side effects. Anyway, I'm sure that in a few years, I'll be giving introduction to Haskell here. Third tip is to organize for change and make incremental changes, because the specification of scientific software, they always changes. If you write generic software, you have a set of specifications that describe what the software is supposed to do. And most of the time, it will not change too much. That's different with scientific software, where you have an idea or an hypothesis, you want to test it, you need to write a prototype function or prototype software that tests the hypothesis, and then you can throw it away if the hypothesis is not correct. So what you need to do always changes. So it's important that you organize your code in a way that changes does not affect you too much. One way to do that is always working from a working state to another working state. So making incremental changes to your code. Sometimes you will need to start over from scratch and refactor everything, but it's important to get always a version of the code that works. Even if it does not do exactly what you want, it must not crash, it must compile if it's a compiled block. Always document the changes and why they were made. So this is very important, so that you know you are able to go back in the past and understand why this change was made or was not made. And of course, for this, versioning tool is very important. And also, you need to look for what we call code smells, which are patterns in the code that should ring a bell and tell you that something is wrong. Here is an example taken from this book. So you see here a piece of code with a code review, just like when you are correcting an exam. People can correct code for other people. And here you see, for instance, that there's a check functionality here, the same here, again here, and again here. And so this is what we call a code smell. It's a clue that something is wrong in the organization or the structure of the code, because you are doing the same thing multiple times at different levels in the control structure. So this isn't a clue that you need to refactor that piece of code, and it will be easier to read if you organize it in another way. Here is another code smell. The for loop goes over the I variable. You see that I is modified here, and there's a condition on I here. So everything here should be in there, because this is where people expect to see the information about the for loop. So this is another code smell, is making it more complex than it should be. Because if all the information was in the first line, the organization of the loop would be easier to read. Where here, to understand when the loop stops, you need to find this part and understand that this one plays a role too. And actually, these are two examples of coding principles that were not followed. The first one was don't repeat yourself. You see that here the same code was here, so it was repeated a lot. But most importantly, don't repeat yourself means that if you have a piece of code that is non-trivial and appears several times at different places in your code, you need to factorize it somewhere, either in a function or in an object, depending on the time of programming languages that you are using. Another important principle is to keep it simple. So example, as before, everything about the loop should be simply in the description of the loop and not split at multiple parts inside the body of the loop. If you don't want to read the book, which is very nice, by the way, there's a single sentence that summarizes, and it's always code as if the guy who ends up maintaining your code is a violent psychopath who knows where you live. This is a very strong motive to code for readability. Coding principles are important, and style is important too. I'm going back to the Stack Overflow, website. And again, here a question which is even more voted than the previous one, which is, what is this operator in C++? I'm asking you the question, who knows what this operator is in C++? If you put this in a C++ compiler, you will see that, or in a C compiler for that matter, it would work. But nowhere in the definition of the C or C++ language will you see this operator. And the thing is that actually you should write it like this. It's exactly the same from the compiler's point of view, but for the human that we are, we understand that actually it's an X with a post-decrement operator and then a comparison operator. And this is really double because it follows the style, which says that the space should be around comparators and that the post-decrement operator should be close to the variable. So this induces confusion, while this sticks to the style and is easy to read. Importantly, the only valid measurement of code quality is the number of WTFs per minute when people are reading your code. If they are surprised or upset every time they read your code, it's a bad code. If they are happy when they read your code, it's a good code. Be aware that nearly every large coding project has a style guide. So if you work at Google, you need to follow their style guide. So how the loops are written, how the curly braces are organized. The kernel, Linux kernel also has a specific style. If you code Python, the important term is PEP8. So there's a whole document on how Python code should be written. And actually, if two professional Python programmers write the same, write code from the same specification, and they follow both PEP8, which they should, they will end up with the same code, basically. Besides the variable names, but the structure and the clarity will be the same. So there are good coding principles, and you should stick to it. Another important thing is to plan for mistakes and automate testing, because when you write something, it works, and then sometimes you will add another feature and it might break what you just did before. So it's important to have tests that you can automate. A very effective way of using tests is to do what we call test-driven development, where you actually first write tests. So you have a piece of program, you have a feature that you want to add. You first write the feature that tests the test that tests the feature that you need to write. So you write the test, you run it, you observe that the test fails because you didn't write the feature yet, and then you implement the feature. You run the test again, and you check that the test passes, and you also test all the previous features that you have included in the code, so that you are sure that in adding that feature, you did not break something in the past. So again, if you want to read more about this, the Wikipedia page is a good reference. But the idea is you write a test, you implement the function, you run the test. If it passes, you run all the tests. If they all pass, you are happy. If one of them fails, it means that you have broken something. And it's much easier to spot things that you break when as soon as possible, rather than introducing an error and then only realizing it a few months or years later. Sixth good practice is to use modern source code management. So nowadays it's mostly Git. There is a session about Git organized by Olivier, so we'll not go into details, but it's very important that you are able to use Git easily to work with others, but also to manage your projects. Seventh is document the purpose and the design, not the implementation. So you know that every language has the option of writing comments in the language definition, and it's important that the comment brings something new to the code and not simply translation of the code in a different language. You see here two pieces of code that are identical, except for the comments. And here you see lots of comments, and here less comments. But here, all the comments, they just rephrase what the code is saying already. So assign base to res, and you see that res equals base. There's nothing new added in the comment. Well, here, there's only one line, but it says that it computes this by iterative multiply for baseline check. And this is important because this part cannot be deduced from the code itself. So it brings actually additional information about why it was written like this, because this is highly suboptimal. So if you're reviewing that code, you should react on this and say, okay, this is not the way you should compute it. But actually, if the command says it's for baseline check, then it's a way to validate why the code is doing what it's doing. Also, if the code simply is redundant with if the comments are redundant with the code, at some point it's nearly certain that the comments will be desynchronized from the code, and the comments would say something and the code will say something else. And if you get to that point, people who are reading your code or yourself in a few months, you will be confused. About comments, you should learn either Markdown or RST. Both are markup languages, so it's a way to write text files, purely text files, with a syntax that makes it easy to the eye when written as a text file, but also easy to compile into another format. So for instance, here, this is valid Markdown, and you can understand readily that this is a title, a subtitle, this is a list. Here you see a link, you understand it, it's quite clear, but you can give this to a compiler, a Markdown compiler, and it will produce HTML, or it will produce PDF, or whatever other format that you want, EPUB or whatever. So when you need to start writing a document, do not use Word or anything like that, to Google Docs, but use a simple text file with Markdown, and you will see that the more tools you use, the more interactions with Markdown you will have. If you have a GitHub account or if you are using GitLab, you will know that in the GitLab command or in the issues or whatever, you can write Markdown and they will be rendered nicely in HTML. I'm at number 8 in my list, which is optimize when it works already. It's important that when you start working, you do not focus on the performances of micro elements in the code, but rather on the global structure. And when everything is correct, then you make it fast. There's no point in making fast something that is not correct. Also, do not try to make it universal for all possible use at the beginning. So it's sometimes a tendency that we have to write code which is universal and we solve all problems. And then you say, okay, but if I put A equals 1 here, it does actually what I need to do for my thesis. This is not the correct way to go, but also do not close doors either. The thing is to get the right balance between the possibility for change, as I explained earlier, and the speed to solution. And this is illustrated here, where someone is asking for the salt, and then it says, okay, I'm developing a system to pass arbitrary condiments, but it takes some time, and it will save time in the long run, but at the moment, this person is stuck. Also, to optimize, you should use a profiler. And we have sessions dedicated to profiling. So profiler is a piece of software that will tell you which part of your code uses the most time. It's important that you rely on the compiler, on the profiler, and not on a hunch or something, to decide where in the code you should put the effort to try to make it faster. You should first find what we call hotspots, like this line here, or this one, and focus on this part, which is the part where you will have the highest return when you manage to make it run faster. There's no point in optimizing a function which is never called. That's the idea. Also, If you have bugs, you should debug cleverly. And again, here there are software to help you debug. So software that will go through each line of the code step by step if you ask it, and that allow you to inspect the content of the variables. Again, there will be a session about debuggers. Very important to know how to use them. You can, of course, try to debug using println or print lines, print commands all over the place, but it's not the best way to work. This is how you work in the optimal way. But knowing how to use a debugger is not the only thing. You should also know several methods for debugging. And there is a very simple method which is called the rubber duck method for debugging. And the idea is that you explain to an imaginary rubber duck each line in the code and explain why it is obviously correct. If you do that, at some point, you will have a doubt. And if you have a doubt, this is where you need to dig and maybe find the problem. If you don't have one, or if you can't imagine one, you can try it with a colleague. Explain orally to somebody else what your code is doing, line by line, and also explaining why it is obviously correct. At some point, if you have a doubt, then this is what you need to dig. If you want a more formal method, there's a Mikado method called Mikado method, which is a setup to try to organize changes in code and also find bugs. It's based on goals, experiments, visualization. So in the process, you would need to write graphs of dependencies and undos. And it's very important that one of the key elements in the method is when you have found a solution to a bug, you undo everything that you did, you go back to the point where there was a bug, and then you apply the only change that you think will solve the bug. So oftentimes when you look to solve a bug, you go from one state, you modify something, it does not work, you modify another thing, it does not work, then you come back to the previous thing, you see that you progress, and then you do a very complex path to the solution. It's important to understand what exactly solves the problems in all the paths, and the way to do that is go back from the past and start again with only what you think is necessary to solve the problem. And this is what the Mikado method allows you to do. Okay, so these were 9 good practices. Do you have any questions about them? No, it's a large number of very different topics, but again, all the references are in the slides. So if one of them piques an interest to you, you can dig deeper and understand how to use them or how to follow them. Next, I want to focus on the shareable aspect of software. And here, the shopping list is a bit shorter, but basically, you need to automate the compiling process because it's not sufficient that your code compiles or works correctly on your laptop. It also needs to compile correctly on the cluster. And to do that, there are 2 main tools, CMake and the GNU build system that you can use for C, C++, Fortran, to actually automate the process of discovering the libraries on the cluster and discovering the path to the libraries that you want to link to the clusters, to your program. So you should start with, of course, creating a make file and having the build process automated. But the way to go a bit further is to use the config and the CMake to make sure that you have a procedure that can be ported from cluster to cluster or from laptop to laptop to create the executable from your code. Another thing that you should look into is what you call continuous integration or continuous development. If you're working with websites such as GitHub or GitLab, they both have that functionality of allowing you to actually compile or deploy your code as soon as you commit something. So if you're not familiar with Git, the idea is that you make a change and then you commit that change and you push that change to the website, to the GitLab or GitHub website. And then the website can trigger actions based on that commit. So you can work in a way that you develop on your laptop, you push a change, and then thanks to all the CI/CD concepts the change is propagated to all the clusters that you have access to. It's recompiled automatically, and maybe some tests are run there automatically. This is all thanks to CI/CD concepts that you can look into on GitHub or GitLab. There's a nice video of Olivier explaining how to use this concept for scientific code on the clusters on our YouTube channel. You should also learn about containers, because sometimes when you have a large number of dependencies that are very strict and difficult to port to the cluster, simple solutions could be to actually package all your code and everything that it needs into kind of a small, complete operating system in a large file that you can copy to clusters and run there. And the way to do that is to use Singularity or Apptainer. And there's a session about Singularity later this year. Third thing you need to do if you want to share your code is to license it. So you need to write a license, which is a contract between you and the person who uses your code, either to control the distribution or forbid the reverse engineering. These are mostly commercial reasons, but also for scientific reasons. If you want to ask people to cite your code, just do the same way they should cite your papers if they're using it, you can do this through the license. And another important aspect of license is protect yourself from liability claims. It's not as important in Europe as it is in other parts of the world. But the way that you are offering something, if people are not happy with it, you should make sure that they are not able to pose you problems because of your code. How you do that is first you choose a license, for instance, the MIT license. I will give two other examples afterwards. But basically, there's a code, there's a text, a ready-made text that you need to copy to adapt simply with the year here and your name here, and put it with your code in a file named license, which is a typical way of creating a license for your code. And you see that this specific text allows certain things, prevents other things, and have some restrictions to it. The MIT license is the most simple and open license that you can use. Here are two other examples, the BSD and the GPL. You see that they have more constraints, but this is a whole topic. If you don't know what to do, you can use an MIT license. If you want more guidance, you can ask either of these people. So in every university, there's an administration about the intellectual property, and here are the contacts you can have in every university. They can help you choose the correct license for your code based on what you want to do with your code. If you are using GitHub, this is related, but it's not per se a license, but you can create citation files in GitHub. And the same way that you can have a BibTeX file to hold information about a paper, you can have a citation file to hold information about your program, your software, and that the GitHub website will format in the correct way for your people to cite your work, depending on the format of the citation that they need. So you give information about yourself, and typically the same thing that you would like to see in the citation in the reference for your code. It's an easy way to make people cite your code. If you want to make your program fast, and you should if you are interested in clusters, there are things that you need to do. And the first thing is to use optimized libraries. And there will be a session about this, but you see here 4 implementations of the same programs with a very old one here and a more recent one. And you see this is proportional to time, to take the time it takes to solve these problems. And you see there's a big difference between old code or unoptimized code and code that is optimized. If you were to write those code by yourself, and it's not your job already, you would be somewhere here. So it's important that you do not implement things that have been optimized by other people for a long time, and try to use these rather than these. But again, there will be a session about this later on. Also, you should choose the right storage, because the computation speed is not only purely computational. The input-output operations, writing files or writing to memory, are also very important in the whole time it takes for a program to complete. So I'm sure you know about files, and you are used to create files, read files, and open files, delete files. But these are not the only paradigms for storage information. There are object stores, maybe you know about AWS, Amazon. There are relational database management systems such as MySQL or NoSQL databases. And on the clusters, most of the time you will go first for writing files, but there are options here that can make your process go faster, because the files operation can be very, very lengthy. And next year we have a session about this. It's important to think parallel from the start. I've been stressing this already. The clusters are parallel machines. Your code needs to be parallel if you want your code to be effective. So for this, you need to make data decomposition or work decomposition easy. So here is a simple example of a small code written in an imaginary language. You see that if you write it like this, actually 2 loops rather than 1 loop with 2 items in the loop, it makes it easy to split those 2 loops and have them work in parallel on 2 different, either 2 different CPUs or cores or even nodes, computers. Also, if you split the loop from 0 to, if you hard code these values and put them in variables, it will be easier afterwards to actually split the split the data into chunks of work for MPI or OpenMP, or the techniques that you will learn in deep parallel programming sessions. So it makes the code a bit larger, but if you write it like this from the beginning, it will be easier afterwards to make it parallel. Also, it's important to make it checkpoint restable from the start. Maybe you've attended the checkpoint restart session a few weeks ago. But again, if you have a loop like this, it doesn't take much more lines to make it checkpoint restartable. So just make sure that you are able to start from a non-initial position, and make sure that you save the result at every iteration or using signals at some point. If you do that from the beginning, it will be much easier to maintain afterwards. Any questions about this? It's a lot of information. I don't think you will remember everything right now, but the slides are there and you can always go back to the slides. And now I will focus on the last part of the sentence, which was efficiently. And I will show you some of the tools that we use that you might not know about, but that make our work easier. And the first one is to perform multi-host SSH. You have learned how to access the clusters with SSH, and you have learned that you can access actually multiple clusters. Maybe you have also access to other clusters that are not part of SESI. But using the correct tool, you can actually connect to multiple clusters. And here I'm using CluSH. You see, it works like SSH, but the thing is it accepts multiple hosts. So if I'm writing something like this, I have now connected to both Lemaitre 3 and Dragon 2. And if I run scontrol version, for instance, to have the version of Slurm that is running, you see that I have 2 lines replied to me with the version of Slurm. Again, if I run Emacs or GCC -v apps. Okay. Again, you see here. So this is what Lemaitre 3 response, and this is what Dragon 2 response. I can actually add more here with Hercules or what is the last one? Nic 5. And actually, I can ask it to, with a capital B, to compact the output. So here again, if I run scontrol version, actually all the clusters have the same version. And you see that the lines are, I don't have one line per cluster, but everything that is common to each cluster is compact into a single line. And if I do the same here, you see that actually NIC 5 has a different default GCC version. And I'm not sure I can show you. No, I can't. I cannot. But believe me, actually, there's only one output for the other 4 clusters. ClearSH can also be used with something like that. You can put the command directly on the command line. You see that there's a little counter that tells you how many hosts it has already connected to. ClearSH should be installed on every CSC cluster, and actually ClearSH is integrated with Slurm. So here you see that I give it a list of computers, but I can also give it a job ID. And if you go to Lemaitre 3 and you have a job that is running, you can use ClearSH and then -I with the job ID, and you will have a connection to all the nodes in your job. So it's very easy to install. It's a Python program, so it's available in every Linux distribution, or if you use pip, you can install with pip. And it's very versatile. So if you don't have it on your laptop, I just encourage you to install it. Another tool that we use a lot is called Ansible. I'm not sure you know about Ansible, but basically it's a configuration management system. And the way it works is that it's able to connect to multiple clusters or multiple machines at the same time, just like you've seen with ClearSH. But actually, rather than running bash commands, you can use already defined modules that can perform interesting operations. And so maybe I can show you. Something like this. So what you see here is I'm calling the Ansible command. I give it the name of 2 clusters. This is a specificity that means that actually inside the list, I want to run what I'm going to run on all of them. And then I'm using the module called line in file. And this module actually looks for lines in a file and can modify it. And here I have the arguments, and this says, okay, there's a file called my file. I want that this file holds a line which reads hello world. And if the file does not exist, I want it to be created. So if you want to write the same thing in bash, it's at least 3 operations, creating the file if it is not there, looking if the sentence is there already or not, and then adding a sentence if it's not the case. Here, it's all hidden in the module here. And so if I run this, you will see that it's connected to both NIC 5 and Lemaitre 3. And you see here for NIC 5, it's changed and the line was added, and for Lemaitre 3, it was not changed because the file was already there. So actually, it's a way to declare what you want to achieve and just let Ansible do what it needs to do to get to the point where you want. And so now I know that on both clusters, I have the file with the line in there. And I didn't have to think about, okay, maybe it's already there, it's not there, I need to check if the line is there and so on. This is one way to use the Ansible. Another way is to play with playbooks. And here, again, I can show you. Okay. So here I have what we call an inventory with 2 clusters, and I'm talking about Lemaitre 3 and Dragon 2. And you see that there's a variable here, max time, which is defined to be 6 hours and 30 minutes for each of them. Then, besides that, I have a playbook, and we call that a playbook, that says, okay, for every host in the inventory, so those 2, I have 1 task, and I can obviously have multiple tasks, but here I have only 1 that says, okay, I want this file copied in the home directory with these permissions, and it's a templated file. What it looks like, like this. You see, it's a very simple submission script, but you see something weird. Here you see max time, which is the name of the variable that we saw before, with the curly braces here. So this is a language, a templating language called Jinja. And if I run the Ansible command like this, so I give it the inventory and then the playbook, and I run it, and what you will see is that on both clusters, the template file will be uploaded. And now if I go to Lemaitre 3, and I look into the file, you see that the variable was replaced with the actual time. And if I go to Dragon 2, you see that we have 30 here while we have 6 before. So with Ansible, you can actually create templated files on your laptop and have them broadcast to multiple clusters with all the important variables interpolated, as we say, based on the variables that are defined in the inventory. Ansible can do much more, but basically, already if you are able to do that, it will be easier for you. Another tool that we often use is Tmux. It's a terminal multiplexer. It allows you to do multiple things, but most importantly, it's a way to overcome disconnections to clusters. So basically, I can show you, and try to show you if I connected here to Dragon 2. I don't know if Tmux is installed. I started Tmux. And now I can work just like if I, whoops. And now imagine that I am disconnected. I am now disconnected. I split my screen. For instance, you lost your Wi-Fi connection or the SSH connection was closed. You can actually go back to Dragon 2 and run Tmux A. A is for attach, and you are back to your Vim session or your editing session. So it's a nice habit to take to always start a Tmux session, or there is also Screen, another program that does the same thing, or Zelish, a more recent one. So they allow you to actually connect to a computer, work, and then if you are disconnected, you can reconnect afterwards and not lose the computations or whatever you were doing. Also, EasyBuild is very important to know about. It's a piece of software that allows you to install software by yourself in your home directory. We use it to install the cluster for all users. But basically, for instance, you see here that I'm looking for Emacs with EB-search Emacs, and I see a list of multiple versions of Emacs that are available to me. And then I can do EB, and then, for instance, I give it this, the last one. And if I wait for 3 minutes at the end, you will see that I have Emacs available as a module specifically for me installed in my home directory. Another thing that I would like to mention is Cookie Cutter. It's a tool to avoid the boilerplate when you start a new project and you need to create directories and so on. I'm just showing you rapidly. If I go to Lumetri 3, and I create a cookie, I run Cookie Cutter and I give it a template, and you see here there are references to multiple templates. Here, the template is called Reproducible Science. It's a generic template. But when I do that, I need to load Python. When I do that, it will ask me a few questions, like my full name, my email address, so whenever you see something in square brackets, it's a default value. So here I don't change the date. I can choose another version, starting version. And then what it has done is in my home directory, it has created a directory called My Project, where you will see a license file. Already, it's a, I don't remember which one it is, but you see that it has put my name here already. If I look into the authors, there's a README already that explains all what was created. You see a whole set of directories created with files created for you. So it's already ready to be committed and pushed to a GitHub, for instance. So Cookie Cutter, there are a large number of templates. Have a look, maybe you will find a template that suits your needs. There are templates for machine learning, for numerous things that help you organize your jobs and your work. The final thing is about backups. It's very important that you organize backup of your data. You need at least 3 copies. For instance, a copy in your home directory in the cluster, a copy on your laptop, and a copy on the USB disk home, for instance. Because we always lose data. And so you must have a way to store your data in a secure and safe way. And for this, you need at least 3 values, 3 copies. If you don't know which tool to use, I can recommend RDiff Backup, which can be used on any operating system that does incremental reverse differential backups. So it only saves what needs to be saved, what has changed from previous backups. So it works a bit like rsync in a way, but it can also encrypt the backups and so on. So very nice tool that you can use. So do you have any questions about this? It was a bit fast, but again, it's a catalog of tools that people use when they need to write software or to maintain them and to work efficiently. We discussed good practices, important choices. I give you an overview of some useful tools, and I'm hoping that you will find them useful. And in all slides, there are practical references if you want to learn more about the topics that were addressed. The final thing is the Philip test, which is a nice test that you could take. It's 12 questions ordered by level of difficulty. For instance, the first one is, do you have a reliable ways of taking, organizing, and reflecting on notes as you're working? This is the first question. The last question is, if you got hit by a bus, can one of your lab mates resume your research where you left off with less than a week of delay? And if you don't score at least a 7 on this list, then there's room for improvement using all the tools that I've presented and also the tools that are in this list.